Okay, so next is 5.18. Use divergent theorem to calculate the surface integral. Okay, so now the information about the sigma, the surface given by surface of the solid bounded by the paraboloid and the xy plane. Solid, and the keyword here, it is solid, meaning that it is understood that we have a closed surface. Okay, so it is bounded by the z equal to 4 minus x squared minus y squared and the xy plane. So xy plane here is z equal to 0. Unless they say that z equal to 1, then you have to have xy plane where z is equal to 1. But in this case, they don't mention that, so we assume that z is equal to 0. Okay, so what is the solid looks like? What is this? What is the surface for this? So it is a ball concave down. So you have a ball concave down. This is on a hemisphere, okay? So, and this is 4. And what is the shape that that we can have on the xy plane? So in order to check that, we have to assume where what happened when z equal to 0. So you have to let z equal to 0. So then 4 minus x squared minus y squared. Then you got x squared plus y squared equal to 4. Then on the floor we have a circle with radius 2. Okay, so now you can see that we have a concave down, a bow which is concave down and covered by the xy plane. So now we have how many surfaces that we have here? 2, right? This the plane, which is the shape is a curve, and the ball. Okay, but in this case, we don't need to use a long way, right? A long calculation, because the Divergent theorem or Gauss theorem can help us. And sometimes in the question they don't mention that you have to use Gauss, meaning that if they don't mention, then you have an option. You have 2 options. So the first option, you just use a regular technique where you have to compute the surface integral, but you have to provide twice, where the first one is the plane on the floor, and the second one is the surface, which is part of the z equal to 4 minus s squared minus y squared. Then you have to total up. But since why we need to waste our time, right? So we can use the Divergent theorem. If they said so, then you have to use the Gauss or Divergence theorem. So in this case, what we want to do is we want to obtain the surface integral using Gauss. So you have triple integral and divergent of f dv g. Okay, so now we have to find the divergent f. So what is f? So f given is x cubed 2 z squared 3 y squared z. Okay, so divergent of f del x cubed plus del z 2x z squared plus del this y del z 3y squared z. Okay, and we got 3x squared plus 0 plus 3y squared. Okay, so then our triple integral now becomes 3x squared plus y squared over the g dv. G. Okay, so now it is go back to the standard triple integral. Okay, so then for triple integral, remember in triple integral, for those who have you have forgotten, then please do a lot of revision on that because that is very important here. Okay, so what is the please refer to your previous notes about the triple integral. Okay, so for triple integral, it is good if you can determine what type of solid that we have. Okay, so now refer to the sketching. So what I told you, the sketching is very important, and just determine what kind of orientation that you are using if you are lying or standing inside the solid. So as a normal people, so you will be standing like that, right? Okay, so now if you are standing like that, who is become which so your feet is lying on which plane? So you are lying on xy plane, meaning that you can have the xy solid. So then we know that your region is on xy plane. Okay, where your region, what is the shape of your region on xy plane? You will get a circle with radius. To how you know that? From this equation. Okay, on y-x plane. So this is your region. So no statement about the first order, right? So please take note on that. Okay, so then since we have a circular region, so meaning that we want to apply the cylindrical coordinate, which is more easier. So now we convert into cylindrical, so we got 3r squared. Okay, and then the dv is r dz dr d theta. Okay, so now limit of okay, for triple integral you have to follow the rule which what on step by step, otherwise it's easy for you to just mix up everything. Okay, so about okay, so actually about the order of integration. So the order of integration, since just now you said that your solid is xy solid, so meaning that your dv is starting from the starting from the dz, okay, and followed by dA, which tell you the region on xy. Okay, so now since you want to use the polar, 2D we call that double integral we call that polar, triple we call that as cylindrical, where for cylindrical we just have extra variable which is z. Z is z. Okay, so now since in this case we want to solve using cylindrical, so we don't need to obtain the dx dy or dy dx, so you can directly just use, so dz dA is r dr d theta, so your dv is r dz dr d theta. So when we plug in, so we got this. Okay, so now we want to obtain the limit. So for the limit of z, okay, the first integration you have to look at from your solid here. So determine the limit of z, who is become your lower bound. So it is z equal to 0, and your upper bound is coming from the Boole equation, where it is given by 4 minus r square. This one, when it is in polar or cylindrical, it becomes z equal to 4 minus r square. So z is from 0 to 4 minus r square, and then limit for the other two you can look at from the region. So theta, we have a complete circle, right? So 0 to 2 pi. And r, how can you determine the r for those who have forgotten? So you have to draw a line starting at the origin and passing through all over the region, and you can see that all of them are starting from r equal to 0 and end up on the same circle, which is r equal to 2. So this is your triple integral now, when we simplify that, okay, so you got 3r cubed dz dr d theta 0 to 2 pi 0 to 2 0 to 4 minus r square. Okay, so now I'm sure that you have no problem, just a simple polynomial. First you have to differentiate, integrate respect to z, so you got z and then replace the limit of z and then so on. Okay, so this is when you integrate one by one, and the solution is 32 pi. Okay, so next we look at the example 18a. Okay, so here the surface is a solid. Again, we have a solid enclosed by the, what is this? It is a hemisphere, right? It's at positive and z equal to 0. So the shape is just like this, but we have a hemisphere and oriented outward, mean endpoint outward. Okay, and f is given. So since now we have a solid, even though they don't mention about the divergence theorem or Gauss theorem, so you can use, and it is better for you to use a Gauss theorem. Okay, because you can save your time. Alright, so now we have a solid where it is a hemisphere, and your sphere is radius a. Sorry, hemisphere. So your sigma is, you got 2 sigma, so sigma 1 is given by z equal to square root of a square minus x square minus y square, right? And sigma 2 z equal to 0. Sigma 2 is z equal to 0, but in this case we don't want to use direct computation, but we want to use Gauss. Instead of double, we use triple. So f dot n ds can be determined by the triple integral of divergence of the vector field G. Okay, so now we have to obtain the grad f. So the grad f is given by x cubed and then y cubed z cubed. So grad f will give you a scalar function. So del x of 3 of x cubed del y of y cubed del z of z cubed. This you get 3x squared plus 3y squared plus 3z squared. Okay, so then we plug into the formula here. So you have 3x squared plus y squared plus z squared dv. Okay, so just like a normal way to compute the triple integral, then you have to determine the name of your solid. So this one is xy, and here is a, you got a. Okay, so and then you are bounded by that z equal to 0, and we are standing like this. So now your floor is on xy plane, so we call this xy solid. Okay, so meaning that your region lying on xy plane. Okay, so for that your dv should be dz dA. A is region on xy. Okay, but before you proceed to determine the limit z or x or y, then you have to look at your solid here. Since now you have a solid which is part of sphere, so it is better for you to solve using spherical coordinate. Okay, so since you want to use a spherical coordinate, so instead of you have to find the z, x and y, we can directly convert the dv into spherical, where it is given by rho square sine phi d rho d phi d theta. Okay, so then we change the Cartesian here into spherical. So 3, so we know that this one will give you rho square. So rho square and multiplied by the dv, rho square sine phi d rho d, d rho d phi d theta. Okay, so your theta. So theta is your origin, part of your origin. Okay, so how can you determine the theta? What is the angle which is lying on xy plane? So you can see that you have a complete circle, right? You got a circle with radius. You got a circle with radius a, and you have a complete circle, because they don't mention anything here about the octant. Okay, so meaning that you have theta, full theta, so 0 to 2 pi, and phi here. Okay, because of your sphere here is not shifted, just the center is lying on the at the origin. So then your phi, remember, is starting for z at z equal to 0. So about the angle here, you have 90 degree or pi over 2. And even though your sphere is shifted, so let's say you have now your what we call that, your sphere move to let's say now it's moved here. So you have a sphere, complete sphere, but now your center is no longer at z equal to 0, but it shifted somewhere. So let's say 1. So 1, then you got 2 here, right? So your phi here is not, when you have phi, okay, when we want to determine the phi, so you cannot just have 0 to pi, because for 0 to pi, if you have a sphere where the center is at the origin, but this one now shifted, so the phi value does not change. Still, you can see that the phi here is lying from z0, z-axis is 0 to, and this one, okay, on the octant 1 to 4, right? Octant 1 to 4. So no sketching on the z negative. So meaning that your phi is not pi like this. So for this, yes, is correct. But for this one, the phi is 0 to pi over 2. Still the same. Phi does not change. Still, for 0 to 90 degrees, so that is for the octant 1 to octant 4. And then for 5 from 90 to 180 down here, that is for the octant 5 to octant 8. Okay, so you have to take note that. Okay, so now we go back to this one. So the phi, because you have hemisphere, so 0 to pi over 2, and your rho is a, right? Your rho is a, so 0 to a. So then we have 3 rho 4 sine phi d rho d phi d theta. Okay, so again, I want you to try to integrate them. Okay, then you integrate. So there is no This is not so complicated. It's a direct integration, so you will get 6/5 a5 pi.